Hi mathematicians, let's do some delta epsilon proofs of a limit existing. Okay, so we are in section 2.7. I think it's precise definitions of limits, but we're really talking about the delta epsilon definition of limits. Right? And so previously we had talked about that a limit exists if the left and right hand limit exists, right? So if the limit is x approached a from the right of f of x equaled L, and the limit of f of x is x approached a from the left equaled L, then we said that the limit of f of x as x goes to a equals L, right? Where on my x-axis we're approaching some value a, I have my function, and then my output here is L. So as we get closer and closer to this value a, right, we're getting closer and closer to this value L is basically what we're saying for the definition of a limit. And also notice, for a limit to exist, we don't even need f of a to exist, right? We have another definition, this delta epsilon definition of a limit, and so basically we're saying for this delta epsilon definition that the limit is x goes to a of f of x equals L if, and so this is my delta epsilon definition here, okay, if for all epsilon greater than 0, there is a number delta greater than 0 such that the distance between the output of f of x and that L is less than epsilon whenever you are within delta of a, right? This is just defining this distance, right? The distance between x and a is less than epsilon, or less than delta, excuse me. That's what it's saying, right? The distance between f of x and L is less than epsilon. These absolute values just really are there because we're talking about the distance. So we're talking about the absolute value of that difference. Okay, so this is our definition. So if we want to show a limit exists, this is going to be our conclusion. All of this is going to be what we have to show and state. So let's go ahead and do an example. So prove that the limit as x goes to 4 of f of x minus 15 equals 1. Okay, so let me go ahead and label some parts of this. So this 1 is our L, this is our f of x, and this is my a. Okay. And so the first part is we want to go ahead and find delta. This isn't part of the proof. This is just part of our like pre or side work. And so when we find delta, we are going to start with f of x minus L less than epsilon. And what we want is we want x minus a less than delta. Okay? And so in this situation, a is 4, so I'm just going to go ahead and write that down there and remind myself that I'm looking for x minus 4. And up here, I'll go ahead and I'll write in my 4x minus 15. And then my L is 1. And so my job is I need to manipulate this to look like this. Okay? And you, depending on the situation, you're going to have to use different tricks. So right now, this one is going to end up working out really nicely for us, because we get 4x minus 16, and I can just take out a 4, and I end up with absolute value of x minus 4 is less than epsilon over 4. I'm saying the distance between x and 4, the distance between x and our a, is less than epsilon over 4. And so then we go ahead and we say delta equals epsilon over 4. And so now we have this relationship here, okay, which is this. All right, so that's part 1. And then after you do part 1, that is when you write the proof. So part 2, the proof. Okay, so if we look at our definition of our epsilon delta or delta epsilon definition of a limit, we get to state this if we show this. Okay, so we have to show everything over there. So actually let me do this. Okay, so you're always going to start with let epsilon greater than 0 be given. Always start with that. And assume 0 less than x minus a, whatever your a is. And so here our a is 4, less than delta, where delta equals epsilon over 4. Okay, so this is how you're always going to start this proof. Epsilon greater than 0. Oh, we took care of that part. Okay, so there has been an epsilon chosen, basically is what we're saying. There's been a distance chosen, and we want to remain that distance away from L. Okay, and so we're going to show that whatever that distance epsilon is that you've chosen, that our delta is going to work. Okay, and so we're saying here we've taken care of this whenever x is within delta of a. We have x within delta of a, and we've chosen our number delta greater than 0. Well, delta equals epsilon greater than 4, which is definitely greater than 0 because epsilon's greater than 0, right? So we have this part, we have this part, and we have this part. Here. We've done this, we've done this, and we've done this, okay? So we have to show this part in the middle. This is what we have to show, okay? That's the part of the proof that we have to get through, right? And after that, then that's it. We're done, okay? So what we're going to do is we're going to start, you always start with f of x minus L, and you want that on the left-hand side. And then you're going to go ahead and you're going to substitute everything in on the right-hand side. So we get 4x minus 15 minus 1, okay? Not a big surprise. And so what do we get? We get 4x minus 16 equals 4 times x minus 4. And so what do I want? Let's not forget about what I want, right? So I want, what do I want? I want this, right? I want a statement f of x minus L less than epsilon, right? That's what, ooh, that's what I'm going for. It's often helpful for me to write down what I want, right? What are my goals here? What am I striving to get? Well, this is what we want, okay? Right now, we've started with f of x minus L when we wrote down what that equals, and we've gotten to this point. We need a way to, one, turn this equal into a less than sign, and two, incorporate epsilon into this relationship, into this equation. What we know is that x minus 4 is always less than epsilon over 4. How do I know that? Well, I've stated that up here. Okay, so if this value here is always less than this, so we have a positive number here, always less than this other positive number, and this is what f of x minus L equals, I can say that I know then that this, if it equals this, is always going to be less than 4 times epsilon over 4. And I think this is one of the hardest things to grasp, is what I just did right there, is transferring this knowledge up here, right here, and changing that to a less than sign. And so what are we saying? I'm saying that I know that this is always less than epsilon. Right? And so that is what we've gotten. Therefore, the limit as x approaches 4 of f of x minus 15 equals 1. Okay? All right, let's go ahead and we're going to do another one that's, I think, a little bit trickier. And it feels very uncomfortable. Where did I put it? Oh, let me see. Give me 2 seconds. It has an x squared. So the limit x squared as x approaches 5. Is that the problem I wanted to do? Let's see. Let's go for it. Let's go for it. Beth's going to go for it. Okay, so we're going to look at another example. Sorry about the delay. I was just looking for the paper, but I can't find it. But let's prove the limit as x approaches 5 of x squared equals 25. That's what it was. I'm pretty sure that's what I was looking for. Okay, so first we're going to go ahead and find our delta. Okay, so whenever we find our delta, we're going to start with f of x minus L less than epsilon. And so what do I have here? I have an x squared minus 25 is less than epsilon. Right? This is my f of x. This is my L. I'm going to go ahead and factor this. X minus 5, x plus 5, less than epsilon. Okay? Let's not lose sight of what am I looking for, right? We want x minus a less than delta. And in this situation, that's x minus 5 less than delta. Okay, so let's see what I have here. I have an x minus 5. Okay, and I know that at some point I am just going to declare delta equal to this right-hand side, right? So I'm not worried about the delta, but I am worried about this x plus 5. We need to do something with it, right? And so I need to make some sort of statement here. I need to make some sort of logical relationship, something I can say about this x plus 5, right? And so, as you know, and we're going to say something about this value of x as we get close and close to 5. All right. And so in general, we know that these values are getting smaller and smaller, right? When we talk about that we want f of x minus L to be less than some epsilon, what we're really saying is this epsilon is going to be like less than 1 probably, right? So I think it's safe to say that we want x minus 5 less than delta. It's pretty safe to say, I think, that this delta is going to be at the most 1. Does that seem logical, right? Because we're getting close and close to 5, right? And delta talks about how close to 5 are we. Well, let's assume that we're going to be within 1. If we're going to be within 1 of 5, that means that we're going to be less than 6. Does that make sense? Right? We're probably looking at x values less than 6. And so I'm going to take that thought, right? So I took this statement, right? I know that I want this x value pretty close to 5. Let's go ahead and say that we want it within 1. That should be a 1 of 5. Then x is always going to be less than 6 and greater than 4, right? We can go ahead and say that. And so if I look then of this range of x, or this domain of x rather, right? The values that x can be. What is the highest this can be, right? What's the highest this can be? Well, the highest this guy can be is 11. So I'm going to change this to x minus 5 times 11. Again, this is very weird. This is very strange. Okay, what did I do? We started with our normal start, f of x minus L, less than epsilon. No problem. Okay. Plugged in our f of x, plugged in our L, no problem. Factored. We love to factor. Can't help ourselves. Factor. Yay! Okay, great, because I know that I'm really looking for an expression with an x minus 5. Well, I have an x minus 5. Fantastic. What do I do with this x plus 5? Okay, so with this x plus 5, I'm going to go ahead and pause this video real quick because I think I'm going to run out of storage. And then I won't have access to this video at all. So I'm going to pause this video here and continue on the next.